Hello. So now we will study the effect of heat onto the solid. So basically we will study when the heat will be given to the solid, when the energy will be given to the solid, what kind of changes we will observe in case of solids. As we already know, whenever the heat is provided to any material, any matter, the atoms of the matter, they gain the energy in terms of kinetic energy or in terms of potential energy also. So their vibration increases. So there are two main types of changes we observe corresponding to the heat given. One change is in the dimensional change, because now the atoms will be vibrating more, so they will occupy more space. Their zone of influence will increase. So corresponding to that, the dimension of the object increases. The second change is in terms of temperature change. So when you provide the heat to the matters, their temperature also changes. So the first thing which changes is the temperature. So when you give the heat, temperature changes. Corresponding to the temperature change, dimension also changes. So here we'll study the dimension change. So when the temperature is increased, obviously temperature will increase or decrease based upon the heat. If you provide the heat, temperature will increase, and if you take the heat out, the temperature will decrease. That relationship we'll study separately. So once the temperature is changed, how the dimension is going to get affected, that's what we will study here. And corresponding to solid, we will study it. And solid we will divide into three categories: linear solid, aerial solid, and the volumetric solid objects. So first we will do with linear solid object. Okay, so we were having a rod. This was the rod we were having, and the temperature of the rod was T1. And at that temperature, the length of the rod was L1. So L1 was the natural length. Natural length means when the temperature was, there was an equilibrium regarding the temperature, meaning temperature was static, it becomes T1 at each and every point, and the length, it becomes static. It is not changing, meaning internal forces becomes zero. There is no tension within the rod at that time. There is no stress corresponding to the temperature. There is no thermal stress within the body. At that time, the length is L1. This is defined as the natural length. So this length is corresponding to the temperature T1. Then what we did, we increased the temperature by providing the heat. So corresponding to every increase in the temperature, there will be length increase also. So this L2 length is at the temperature T2. And this L2 is the natural length at T2, meaning at this time also there is no thermal stress. So you increase the temperature, then you wait for some time till the thermal stress goes away, till any stress goes away. At that time you will find some increase in the length. Okay, so initially the rod was of length L1 from A to B. You increase the temperature, rod went from A to B dash. There was a change in length of delta L corresponding to the change in temperature. Okay. So here, in this case, when we make the formula, there is a pretty simple formula. The formula in this case, which is applicable here, is L2 is equals to L1 1 plus alpha T2 minus T1. That's the formula. From where we get the formula? This formula is empirical in nature. So basically what we observe, we perform an experiment. We perform the experiment with different types of rod, different material. And corresponding to each and every material and each and every linear object, we come across that fractional change in the length of the rod. Fractional change in the length of the rod is proportional to temperature change. Or we can say, when we perform the experiment, we come across that L2 minus L1 divided by L1. That's the fractional change, delta L upon initial length. Fractional change in the length of the rod was proportional to change in temperature, which is T2 minus T1. And as you can see, if the T2 would have been less than the T1, this fractional change would have been negative. So the length will decrease. So the fractional change in the length of the rod was proportional to the temperature difference, and this, while doing this experiment, the temperature change was not that much, meaning this formulation, this empirical formula was valid for a small variation in temperature, not for large variation, small variation in temperatures. So there was this proportionality constant we are seeing. This is a proportional sign. So we have to introduce a constant, and that's not this is not a universal constant we will introduce. It will be a local constant. So L2 minus L1 upon L1 will be equals to, after introducing the constant, and that constant is defined as alpha T2 minus T1, where alpha is the local constant which depends upon the material of the rod. What kind of material we are using, it depends upon that. So if you rewrite this equation, if you rearrange this equation will convert itself into L2 is equals to L1 1 plus alpha T2 minus T1. That becomes your final formula, which is valid for small changes in temperature. Here this alpha is defined as coefficient of linear expansion. The value of alpha will depend upon the internal property. It will not depend upon the dimension. Dimension is already covered. This alpha will depend upon the material. Basically, whether you use the copper or steel or iron, what kind of material you are using, depending upon that, we have the value of alpha, which is constant, pretty constant. Which the value of alpha is pretty constant. For all practical purposes, we assume alpha to be independent of temperature if the temperature variation is small. But for large variation of temperature, this alpha also starts depending upon temperature. That's why this condition is there. Because if this condition is not there, this alpha will not become constant. It will not remain constant. It will become dependent upon the temperature. So this formula will become a little bit more complicated, which we don't have to do. So for all small variation, this formula is valid. Okay. So alpha is a coefficient of linear expansion, and from here we can get the length, final length, corresponding to change in temperature, which will be happening corresponding to any heat given. Okay. Thank you.